Today we're going to talk about the second technique for unsupervised learning methods. So last session we talked about clustering using K-mean clustering. So now we're going to see, we're going to have a few sessions on density estimation. So there are a variety of techniques to accomplish that density estimation. So we talked about it mainly today with two of them. So using histogram based methods and also K nearest neighbor. And for the next session we're going to be talking about the other techniques for density estimations and a well-known algorithm called EM as well. So as just a recap for the previous lecture, so we are dealing with a bunch of data in D space. So we have a data set of D containing x's from x1 up to xn, and they are having no labels. So we want interested in gaining some information to group them in a way that they are similar to each other, right? So in this case, our x's, xi's are generated from IID distribution with a certain, probability. So what is IID? IID is the abbreviation for identically distributed and independent distribution. So I'll have a look at the formal definition just a second. So we have several x's that comes from a certain distribution, all right? So we want to find an output p hat of x, which is an estimate of that probability as to what was the probability of that density estimation given those x's. So we want to understand the different distributions. So we have a bunch of data here. So say you are dealing with one-dimensional space. So you have a bunch of data in that 1D space. So you want to understand the density of this data, and you want to accomplish that task so that when you draw the graph, either in a curvature mode or in a sharper way like this. So the more data you have, the higher the density on that specific axis would be, right? So in this case we had two set of data here. So the curve or the sharp square would spike higher than these two, and the rest are normally spike lower, right? So we want to find an output of an estimate of this distribution. All right. So just like this, here we have 7 x's, so x here, and then we want to find a distribution corresponding to that. So we want to match it like this. So that was the real estimate. We want to find a p hat of that is close enough to that. Say something like this. So different techniques are giving us different curvature and different shapes. So some techniques are giving us more granularity like this, more curvature, so more fitting. The other techniques would give us like spikes like this or this. So each of them has its own applications. But in general, we are interested in estimating the density, estimation. All right, so let's talk about the definition of IID. So we call a distribution IID if it has these two conditions simultaneously. So identically distributed and also independent. So we call it identically distributed if and only if for every x in R space, if f of x of x would be equal to f of y of x, right? So we understand that if this condition holds, they are identically distributed. So how are we going to define the independence property here? So we call it independent if and only if we have if x and y of x and y, and we can chunk it up into fx of x dot fy of x. So that means that these two were independent from each other. So you could aggregate it this way. And both of them are if and only. So you can either go from this way to this way or from this way to this way, right? In both cases. So if these two conditions hold, we call this IID. So one of the easiest and more commonly used applications of this density estimation is finding, you have a bunch of data and you want to find the certain discrepancy within that data, right? Like anomaly detection. So this is A, anomaly detection. So this could be done in within operating systems, within antiviruses, maybe malware detections, or bank fraud as well, right? Yeah.
The capital F, is that the CDF?
What is it?
Like, is that the CDF fact? I forgot what I called it.
Which layer?
Like a capital, yeah, F, is that like the CDF of X? Like the continuous probability distribution or something?
Oh, continuous could be or could be not.
Because I just remember like the capital F, and then the bottom one was the joint probability distribution, something like that.
Yeah, they have similar properties, but not in all the cases, right? This could be continuous as well.
Yeah, no, because there was a PDF and a CDF, I think, and then I think there was like a lowercase f that was the PDF.
I see. I should double check on that. Yeah.
I just forgot.
So yeah, maybe we are mixing up the notation, but just consider it as a function here.
Okay.
I guess. Right. All right. So any questions so far? All right. So let's talk about the first method now. How are we going to accomplish this task? So we want to find p hat of x. So the first technique is called histogram method. So assume we have a function p that is non-zero over a bounded intervals of x. So in most of the density estimation kernels or techniques, we usually have to have the bounded property. So we can't just talk about unbounded data because we want to make sure, because unbounded data will prone to have another unknown estimation of density, and which is going to lower our accuracy in this case. So let's talk about histogram here. So we have 4 data points here. So these are our data. There's x's. Okay. In 2D space, x1 and x2. So in histogram base, we are talking about a uniform size for our B cubes here. So we call them hypercubes. So we have B1, B2, B3, and B4. So, and D is 2 here. I'll talk about it. Now, if you want to mention the density and the probability of having x's within each of those hypercubes, right? We're going to say that, okay, B1 contained 2 of the x's, B3 contained 1 of the x's, B4 contained 1 of the x's, and B2 was having none, right? So, as a notation as well, we call the volume of each of these uniform hypercubes with V represents the volume. So easily we can see that if you want to distribute this density estimation in each of these B's, so this B must have a higher value because it contains more of the X's, right? So 2 out of those 4s, I would say, this would contain 0. This would contain 1 out of 4s, and also this one 1 out of 4s, right? And since these 4s, these B's are uniform, if you were to transform them into that previous shape we had, like this shape, our curves would be something like this. Right? Because these are representing our B's. Right? And these have a uniform area. They're square. So we would have to assume that the output would become something like this. But let's see if it becomes or not. All right? So I brought the figure there on the upper right side. So the estimate for all those x's for B1 would be 1 over 2, and this V was referring to the volume of each of the B's, right? The hypercubes. So I'm going to just mention here. So whatever the volume was, you're going to just have to multiply it to that. It's just a variable you can apply later on. So B2 contained nothing. So the P hat, the estimate of probability is going to be 0 here for all the x's within the hypercube of B2. On the third one, we have 1. And on the fourth one, we have also 1. So 1 out of 4, which becomes 1/4 of V, right? And we can see that the real probability was the same here. So our density estimation was correct here. So that would be a very simple and intuitive example on histogram. So we just populate our density estimator using the number of occurrences that each of those x's were within our hypercubes, right? All right, let's see if we can expand this to a general case if you want to have a definition for that. Okay, so let Ni be the number of samples in each of those hypercubes. So on our previous example, it was 4. So the real probability of x within that hypercube of B would be simply the fraction of ni's within the overall n, right? So say we had 1. So here. So we had 1 here out of 5. N was 5 here. So it would become 1/5, right? So the p hat, the estimate that we want to make sure we find is 1 over v, the volume of that, multiplied by ni divided n for every x inside the bi. All right? So that's going to be a simple general case for the histogram based method. And for this v, since we were talking about the 1D or 2D, suppose if you have a higher dimensional space, so this v would expand to that higher dimension. So it's going to become, so if you talk about those squares, it's going to become spheres and then higher dimensional spheres as well. But here, for simplicity, we just talk about that v in lower dimensional space. All right, so another example. So say we have our x's are within the window of 0 and 3, and d is 1, so one-dimensional space. And here are our x's. So we have these two. So I've shown them in blue. You have 2 here, 1 here, and 2 here, right? So using the histogram-based method, we had overall 5, right? So the n was 5, and in this case, ni was 2, and I equal to 2 was 1, and was 3, right? And since in hyperhistogram methods, these b's are uniform, so these 3 are equal, right? And for the case of the ni equal to 2, so we have 2 over 5, which brings this spike higher. And this comes at 1 over 5th. Again, we have 2, so it would become 2 out of 5th. So it becomes something like this, right? So that's the p hat of x as the estimated probability distribution of this. All right. So now we see that using this very simple method, we can estimate the density distribution. So, but still, we are facing a trade-off here. So, because the more we go fine grain, the more we want to, estimate in more fine grain. So, make these things smaller, thus higher granularity. So we have to have more of these hypercubes, right? And also one of the disadvantages of this histogram-based method is you cannot have avoid these sharp corners, right? So what if you wanted to estimate you wanted to estimate it in more fine grain using the curvature shapes like this? So we need to find another technique for that we're going to discuss as our second technique, which is k-nearest neighbor, right? Okay, now after this, we finally can say that our hypercube B1 had 0 and 1, so it was within this window. B2 was within this window, and B3 was within this window. Okay. So the final p hats are 2 over 5, 1/5, and 2/5. All right, so as I mentioned, the smaller the bins are, the more granularity we can expect from this, but it would become more discontinued, right? Because we want to go, in this case, we go up and down more. The continuity will be less. And also, for higher dimensions, if you expand it to higher dimensions, because we are lacking this curvature shape, many of these BIs, many of the hypercubes, will become empty. All right, now let's talk about our second technique, which is k-nearest neighbor estimator. And let's see if that one can help us better with, more fine-grained shapes and more curvature. So here, rather than using uniform hypercubes for our B's, right? We use the distance of the k's nearest neighbor. So this is k. So we use only the distance to determine the volume for the region. And that's why this approach is called sometimes k nearest neighbor, or KNN sometimes. And this k comes from the number of nearest neighbor you want to contain or you want to take into account. So that's a hyperparameter as an input for this model. All right. So at each of those points, we are trying to understand the surrounding data, and depending on the k, we want to take into account those number of k's which are the nearest neighbors for our current node. So again, having a data set of D containing x1 up to xn, this is n. So let x1, x2 up to xk, well actually, yeah, because we define it as k, here is this k. Be the k's nearest neighbor of x. I'll show it visually in the next slide for you guys. It's pretty simple and intuitive. All right. So we calculate the distance from each of those x's, each of those x1 of k, so k could be anything, or x2k. So say we have these 2 points and we're here, so we need to calculate the distance between our point and that point, right? And it's simply the norm of that, so that x between x1 and x2 is just a distance, and we call it lambda, or whatever you want to call it here. And in k nearest neighbor, because we are in a 2D space or high dimensional space, we would be dealing also with the volume of the spheres or circles, or in one dimensional, just one straight line in RD with radius of this. So suppose this was in 3D space. So you wanted to have something like this, right? That would be the radius, which comes from this lambda, and that would be the whole volume, right? In 2D space, it would be like this. right? And in 1D it would be just a line, right? So these two. And in higher dimension also we cannot visually show it to you. All right, let's just have an example with two set of data in R2 space. Okay. So say I'm here, I add a new data here, okay, and I assign k as 3, okay. So now I have to find okay, just have it this. So I have to find the 3 closest data to my current node. So what's going to be this 3? It would be 1, 2, 3. These 3 are the closest one, right? Here. So I draw a circle here because it's R2 and I'm here. So these 3 are my closest or nearest neighbor and my current position is here. Okay? So now, the radius would be this. I mean, I should have made it like here. So that the radius becomes this. And now using a majority vote, within this radius, and this square or sphere that comes out of that, I got 2 reds and I got 1 blues, right? So the majority tells me that since I have 2 of these reds and 1 blue, this new added data could become another red, right? If I was here, instead of that, if I was here, and my k was 3, so this would become like this, okay? That was the radius, the x's. And using a majority voting, I had 2 blues and 1 red within my k equal to 3. So this would become also blue as well. So blue. But this become red. All right. So this is pretty simple and intuitive. So this is for 2 set of data. If you had only 1 set of data, that would be even easier. You would just be able to just cluster them, or define the estimated density out of those. Is it clear? So in a 1 set of data set, when you just have like blues here, x1, x2, and x3 for the k equal 2. So now when you're here as your current node as x, so your 2 closest neighbors, that's why k is 2. Your 2 closest neighbors are x1 and x2. You don't consider x3 in this point, and you would just find the radius from x to x1, which was the further point, and that would be your circle, right? So this is another example when you have only one type of data. So this would become a density estimation. This would become a classification. Okay. And using k and n, right? So we are mostly interested in this tech because in using nearest neighbor, we can apply several other tasks with that. So the thing that we are interested mostly here in this section is only density estimation, not the classification. But just to let you know that you can apply nearest neighbor to classify new data as well. All right? Okay, so let's talk about the definition of the p hat here. So just like the histogram, our estimated p or p hat is related to in an opposite way or in an adverse manner with the volume of the k, and the k could be 1, 2, or n, or anything that we input to the nearest neighbor algorithm. And in order to make it equal, we apply this c as a constant. All right? So this is called normalizing constant. And the v is the volume of each of those spheres that generates out of the k nearest neighbor. Okay? So c, how are we going to choose c here? So c is chosen by normalizing p hat so that the integral of the summation of the p hat, which was the probability, estimated probability of dx, would be equal to 1, because we're talking about, say you are like here, so that would be the estimate, and this should be bounded again, so you have a bound, so within this point this should be equal to 1. So using the histogram methods, we would be generating something like this, right? Here. We're more cube. All right. Most of the cases you don't have to calculate this integral. So I try to say it's often not required. You just have to mention this is c and use it just as a variable. So in the case of k2, let me just recap it again. So you're here, you find your two closest neighbor, which is x1 and x2, and you draw this circle or sphere in the higher dimension, and that would be the radius, and the volume is going to be the volume of that circle or sphere. Okay? So now let's see a bunch of examples for nearest neighbor density estimation now. So we have a bunch of data, d1, 2, 4, and 7, and our d is equal to 1, so one-dimensional vector, and the bound is from 0 to 8. Okay? So your data would be like this. So you have 4 points, 1, 2, 4, and 7. Only one dimension, so vector space. You wanna apply nearest neighbor to find the density of this data. Suppose k is equal to 2. Or let me just give you the example for k equal to 3 because it's easier, and then we go back to 2. So the same data, k is equal to 3. So what does it say? I'm here. Okay, say I'm here. I want to draw this point. Since k is 3, I need to find the 3 closest neighbor within my current location, right? So it would be like this. Right? I'm here, or here, or here, no matter, because we have only 4 points. The other case would be this. Or this, right? And if you combine these 3, the shape would become like this. So your neighbors, nearest neighbor at this point would be 1, 2, 4. So these 3 points. If you come it from this side, if you take a look at it from this side, your 3 closest points from 8 is 7, 4, and 2, right? So 2, 4, 7 on this side. Okay? So that's why you have these two spheres here instead of hybrid cubes for the histogram. So how did we derive to this? So we don't want to calculate the C constant. We just point it out as C. So here, this is going to be divided by 1.5 because the starting point was 1 and this is 1.5 up to 2.5, right? This would be 3 up to 4. That's why you have it C divided by 3. On the other side, also 4.5 here from 1. From here would be 6 because it's 1 to 7. What else we have? We have 2.5 here, and 2.5 will start from 7 on the other case. I'm talking about this case. So 7 to 4.5, the distance would be 2.5. That's why this becomes 2.5. All right? And this shows the p hat. So this is the axis for that. So C fourth shows that you got 1/4 of the data here at this point, and more points here, more points here. Okay. So now that's the case for k equal to 3. So we call it KNN. Now let's go back to when we have k as 2. So this becomes 3 because we are taking into account 2 closest neighbors. So we're going to have this, we're going to have this, and we're going to have this, right? So instead of 2, we're going to have 3 on the other case. All right. So now k is 2. So we start again from these points, 1, 2, 4, 7. Now since the k is 2, I'm going to have 3 of these NNs because my closest neighbors at this point here were these 2. At this point here was these 2, 2 and 4. If I'm here, my closest neighbor will 4 and 7. So I have 3 of these. And these curvatures will become more discontinuous, or we're going to have more of these because we have more NNs, so more nearest neighbors. So just like before, so when you are here, starting from 1, that would become 1.5. That's why you have C over 1.5 here. If you are at 2 point, so starting from here again, so now from here to here, so you start from 2, and this 3 would become the distance 1. So that's why you have C over 1. And just like that, you have another one, C over 1.5. So in the case of K2, we had these 3. So the first one, 1 and 2, the second one, 2 and 4, and the third one, 4 and 7. Okay? Let me clean this up so you can see it better. So as you saw, one of the prerequisites to apply this density estimation is, first of all, you have to have a bounded data. That's why you have this capital X here. Shows the bound. And you can play with the hyperparameter of K, or on the other technique, which was histogram, the number of B's, to generate higher or lower level of granularity. So depending on the way you want to have your estimated density, you're going to have some hyperparameters to play. Okay, so then some notes. Again, the larger the K is, so the smoothest output you're gonna have, right? So if your K would be like 10, 12, so those curves are gonna be smoother, like this. Whereas your K's are small, you see they have more sharp peaks. What if K was 1? What would happen? So you had a bunch of data here. That was your bound, okay? And K is 1. What would happen? You have a guess? Any guess? Take a guess.
You can just get like rectangles in this case, one.
Rectangles.
Rectangular shape.
Like this way, or this way.
Vertically for like the nearest each point, so you've got just I don't know the distance and the points just be
Right. And yeah, it's almost correct. That's right. So if the K was 1 and you have a bunch of data, it would just become one spike, and so it would be sort of almost a line here, like this. So you add this and then one spike there, sort of in a simple line on a K1, right? So they call these functions impulse functions. Just to let you know, impulse. So it's gonna be like this, just simple line, and the estimate would be something like this. Okay. Just get rid of this. Okay, and the properties, as I mentioned, so works only on bounded impulse space, and just like before, is a non-parametric and used. And the convergence theorem holds. So with this method, we can converge actually with certain conditions. All right, so I'm done for today. I don't want to stress you more. You're going to have a midterm. So we will continue our density estimation using Gaussian kernels on Monday. And yeah, we'll carry on. We'll go there from that point. Right, guys, so all the best for your midterm. See you tonight at 6.